couple of people who are not students. And so for those who are not students, then we require that, except if you have incredibly clever comments, maybe you can put them out. But this is not for you to go and promote your own interpretation of all of this. This is a warning for the postdocs and other people who are in some corner of this room. And I won't be shy about it if you do so. And don't be shy too. So this is a course which is a bit different than the typical course that you usually have in science or in mathematics. I think of courses in science where you learn about some physical phenomena of nature, then you learn about the mathematics which is related to it, and then you get evaluated by how good you are. Then you play the mathematics, and then you put a few words which says that corresponds to some physics phenomena. This course is going to be a bit different than this, although will learn, or at least will bridge gap, or Joseph will do this, bridge some gap on the mathematics that you might have. Really, this course is a conceptual one. If you want to try to understand how do the symbols and the theory kind of link with the reality of the world in which we live, and trying to kind of make sense of the theory of quantum mechanics. And when we do this, and we try to think about this, there's no essentially right or wrong way of doing it, at least that we know today. And maybe at the end of this course, you will come with the right way of thinking about quantum mechanics. And there is some gold in there is that you really start to think about what does the theory of quantum mechanics mean for the world in which we live. But the fact that there is no right and wrong at present means that it is very different than just kind of write an equation and being able to solve it. So you have to do a lot of thinking, wondering, is this the right way of thinking about the problem, or thinking about it, looking at it? Is there a different way of doing it? Is it better to do it in way A, B, or C? And in order to kind of bring these different point of view, the course will be structured in a way that you'll have a few courses which will be some background material. And after that, a series of lecturers will come here and be proponents for one particular interpretation of quantum mechanics. They will come and say, I am a proponent for proposal A, and then I will try to convince you for 2 lectures that this is the right interpretation of quantum mechanics. Your role in this is to listen to it, and part of your role will be a little bit like being part of a jury. So listen to the person in front and decide at the end of the term or the course if that person is guilty or not guilty. Not guilty, or maybe saying guilty of passing some fast one on you. So your role is to be attentive, to say, does that really make sense, this particular interpretation of quantum mechanics? And to challenge the lecturer who's in front, if you do not understand it. So if you do not understand part of it, if they come and say things which seem to be incredibly complicated, and you say, how does that work? Your role is to stop the lecturer and say, hey, this doesn't make sense. 4 years ago, we had the first incident of that course, and it was a pleasure for me to, at some point, stop the course and say, hey, okay, we need a break here between the lecturer and the audience, which was giving quite a hard time to one of the lecturer who came. So with my Latin temperament, I hope that this will be repeated. It will be a nice challenge here. But this is really the goal of the course, is for you to understanding the conceptual part of science or foundation of quantum mechanics. So very different modus operandi for this course. For this, the course will be evaluated in a different way. 20% will be on participation in class. So today your picture will be taken by the nice little camera which is there. And I'll put numbers next to faces, and I'll pass it on the next course, so you can put your name there, and then it'll be my job. And there's a few students of mine here who will laugh. I will have to remember your name and the number, and then kind of who will be evaluated on participating. Again, there's no right or wrong question to be asked here. Really kind of comprehension and challenging the person who's in front is part of what you're supposed to do. There'll be 30%, which will be semi-assignment, just the traditional part of knowing some mathematics and kind of procedure related to basics of quantum mechanics. And the last part will be a project. And the project could be things we'll explain a little bit more as the course goes. In the project, it could be summarizing a few of the interpretations of quantum mechanics, or pick one and advocate for or against it. So you can decide which one you want to do as the course comes in. I will now pass the rein to Joseph, who will start the lectures and talk a little bit more about the detail and the motivation. But 10 minutes before the end, we'll make a short survey of who came here by car, ride, and everything. And so if we need to adjust time at which we start and leave and things like this, then we'll do this. And because there might be a few people, right, we decided that doing this at the end instead of the beginning would be more helpful. So until we arrive around 10 to 4, don't run away. And if you want to have help on finding a ride here. So Joseph.
Thanks, Raymond. So I agree with Raymond that, I guess in my case at least, I'm not 100% certain that I can, know the right way of thinking about quantum mechanics, but I will try and convince you there are some wrong ways of thinking about it. Okay, now why can't I make this maximum screen? Cross participation marks right there. Okay, yeah, so at the end, we'll turn to some logistical issues about grading and marking and other issues of transportation. But for now, I guess we'll get into the material. Oh, so actually before, now that I just figured that out, let me just point you to the course webpage. So you can't actually see the full URL here, but if you go to the IQC webpage under activities and then courses, you can find all the information you need to navigate the course, the locations and so on, as well as the schedule of speakers. So for the first 3 weeks, I will be going over some essentially background material, especially the first 2 weeks, where we're going to go through the mathematical formulation of quantum mechanics, and followed by some basic problems of interpretation. So we'll cover a lot of the historical issues between Einstein and Bohr, and the way von Neumann and Dirac formulated the interpretation of the theory, the EPR paradox, Bell's theorem, and related issues. We'll also talk about, constraints on hidden variables includes Bell's theorem and contextuality, which we'll discuss. Then after that, Robin Blomkahut, who's here in the audience, will give you a week's lectures on probability and its interpretation. So I'm staying away from that topic with a 10-foot pole, as you'll see explicitly in today's lecture, and leave it up to Robin to sort that out. The issue actually, when Chris Fuchs will discuss the quantum Bayesian view, which is intimately tied with that topic. And so then after that, we'll have Gregor Weiss talk about some experimental tests of Bell inequalities. So, I mean, it's important to emphasize that interpretations and foundations isn't just a theoretical exercise, that there are experimentally relevant issues. And so we'll see that both in week, 5, as well as the last 2 lectures where Tony Leggett and Michel Devoret will discuss macroscopic quantum phenomena as fundamental tests of quantum mechanics. And after Gregor, in the week of February 22nd, Alex Wiltshie will discuss convex sets framework for probabilistic theories, which gives kind of a broader framework for understanding quantum mechanics as a special case, a broader theoretical framework in which quantum and classical theories emerge as particular cases, is what I meant to say. After that, Roderick Tomolka will discuss Bohmian mechanics, sometimes called the de Broglie-Bohm interpretation. And then the TBA is, Jim Hartle was supposed to give us lectures on decoherent histories, but due to health issues, couldn't make it. So we're trying to find a replacement lecturer, probably a mini worlds person, but we'll have to see what we can come up with. If you have any suggestions, please feel free to make them. And then somewhere in here, hidden is reading week, where there will be no lectures, although it's not listed. But, oh, I think it's February 14th, the week of February 14th. OK, great. And so please do ask lots of questions, and when you do speak up, so we can be picked up by the mics. So what I'm going to do today, hopefully today I won't get past here because this is actual virtual notes beyond there. So I decided to do all these things using Beamer, and it's a new experience for me. So it took a lot of time to lay this out. But these notes, the first 2 sections here, first we'll cover the just standard axioms for quantum theory, followed by the generalized axioms. And for the section 2, I'm drawing heavily on the fourth-year quantum course, which you all should have had an equivalent to. And this is drawn from the initial chapters of the Open Systems course that I teach at IQC. So, but before that, I thought we'd have some motivation for why even worry about this. So in my view, and you don't necessarily have to agree with this, one of the purposes of this type of material is to gain a deeper understanding of what kind of theory quantum theory is, and what does it tell us about the world. So one of the probably most fundamental questions of interpretation and foundations is, what is a quantum state? And so you'll hear a surprising variety of answers to that question over the course of the term. And to get a little philosophical on you now, one of the things we want to know is, what can we say about reality, about the nature of reality? And kind of the philosophical term for that is ontology. So what is the ontology of the world in light of quantum mechanics? And that will come up again and again. And what you'll find is that some people will actually tell you that there is no reality at all. And others will tell you that there are many parallel realities. So it gets somewhat perplexing at times. One of the really neat things about foundations to me is the fact that if you do kind of start with the assumption that there is some reality or some ontology, then what you find is that that ontology has to, we know for sure based on experiments that ontology has to satisfy certain constraints. Most importantly, it has to be non-local, it has to be contextual. So we'll learn about that in detail. So another amazing thing is that you can actually do quantum theory. You can be a user of the theory without ever worrying about these issues. So a quantum technician, so to speak. So why then worry about them? So, well, of course, intellectual curiosity. So the main goal of science is to be able to predict and control things, something I kind of came to terms with sometime during graduate school. But as scientists, I think a lot of us really want to know how nature works. It's more than just a practical venture. But tied into that point, as far as practical advances in research, it's my belief that understanding basic issues of quantum foundations and interpretations allows you not to miss opportunities for kind of breakthroughs in research. So I think there are many examples historically of people who use quantum theory who have a very unsophisticated or inexperienced, lack of familiarity with foundational interpretational issues, who kind of were led astray in analyzing certain phenomena. I will discuss the example of quantum chaos in particular as an example of that later on. And I think also it's clear that many major advances in quantum information and its application to technology were born out of very smart people worrying about these issues. In particular, what is superposition and what is entanglement? So a case in point about that is quantum information and quantum computing, where there's a clear, you can trace back the history to people like Einstein and others worrying about what does it mean when states are entangled, showing that there are unusual properties if you want to think about things ontologically with entanglement. And, well, that was Bell's point, as we'll see. And what you find is that people don't appreciate, a lot of researchers don't appreciate that, it was these concerns about these fundamental questions that really gave rise to the realization that there was something special going on with quantum mechanics and that that specialness could be exploited. And of course, another overarching issue, which I don't know very well, but believe quite strongly, is that understanding quantum mechanics deeply is crucial to making advances in unifying quantum theory with general relativity. I mean, it's been basically almost 100 years that, in principle, we could have done this, and that it hasn't happened. And so, my view is that it's because the people working in this area may not have asked themselves to answer carefully the question, what is a quantum state? And the answer to that could help advance the unification of our two fundamental theories. So I'll open the floor to anyone else who wants to put forward some reason why this is interesting to you or you think it's important. And even more senior people are welcome to chime in. Any takers? Chris, I thought for sure you'd chomp at the bit for that.
I think it's scary.
It's probably that somebody disagrees with all my motivations. All right, fair enough. So hopefully that motivates you more than the fact that you've already come out of your way to come to this lecture. And anyhow, but before we can turn to these subtle issues of interpretation, we really have to be clear on the formalism, and particularly the mathematical formulation of quantum mechanics. So now we get to something very concrete. So as you saw from the outline earlier, I've divided the axioms into these ideal axioms or standard axioms, followed by the generalized axioms. So I think I'm in a minority of foundations people who really, I think the idealized axioms are what you should take as primitive. But a lot of people take the generalized axioms as what should be the starting point for defining our theory. So I'll present both independently, and then you can decide yourselves. Yes? Yeah. So as you all know, if you prepare a quantum system, then we describe it's an ideal preparation, meaning it's error-free, and it's a case of maximal knowledge consistent with quantum mechanics. Then the preparation is described by a Hilbert space vector, often called pure states. So I think, as you'll see throughout the term, it's actually crucial to be careful about what exactly the term state means. So I prefer to use the term preparation to refer to the fact that a quantum system has been prepared according to some procedure. In particular, because the word state has a certain ontological connotation that I don't espouse. So it's just a notational thing. A Hilbert space in finite dimensions is a d-dimensional complex vector space. We have normalization, which actually gives us geometrically a sphere in the sphere 2D minus 1 in 2D real dimensions. That's just a simple constraint on the coefficients. And of course, as you know, the overall phase of a Hilbert space vector is physically insignificant. So in reality, there's a one-to-one correspondence between distinguishable preparations and elements of the complex projective space of d minus 1 dimensions. So basically, you look at these superscripts and just think of them as counting the number of parameters involved to characterize the state. So if it's a complex space, then you have d minus 1 complex numbers. And for the sphere, that's in the real case, so it's 2d minus 1 real parameters. So for measurement, we want to consider self-adjoint operators, where we'll denote the operator A to have eigenvalues A sub L. And the eigenvectors are denoted by a double index because of the possibility of degeneracy. So if AL is a degenerate eigenvalue, then there's more than one eigenvector associated to it, which defines the rank of the dimension of the subspace of the degeneracy. And one of the most fundamental things you need to kind of do calculations in quantum mechanics is the spectral decomposition, where we express A in terms of its projectors, weighted by its eigenvalues. And the projector is a sum over rank 1 vectors, where ML varies over the dimensionality of the subspace. So given that definition, we can write down axiom 2, which is that the set of observable outcomes, if we measure A, is specified by the eigenvalues, and that the probability of finding outcome A sub L is given by the trace rule. So axiom 2A is what gives us the kind of structural features of the world in light of quantum mechanics, namely the quantization of observables, which basically means discretization. And axiom 2B is known as the Born rule, and it gives us the statistical / probabilistic / indeterministic character of quantum predictions. So here's where I start upsetting Chris. We can replace the term probability in our definition, which is, I mean, most textbooks just call it probability. But, and this is kind of something provisionally I came up with this past weekend, is just to replace it with relative frequency. So rather than define the Born rule as a probability, just define it as a relative frequency. So I'll be interested to hear why that might not work. Because at the end of the day, quantum mechanics is an empirical theory, and we can only compare it experimentally to sequences of outcomes, which of course gives us rational numbers. So does this mean we can banish the term probability from the formulation of quantum mechanics altogether and cancel 2 weeks of lectures? This is definitely an enticement. Come on, you can't hold back now. Chris, do you think this is a reasonable move to just drop the word probability in the Born rule? Just trying to get some feedback because it's feeling too much like a monologue for me. Just throwing in these. Next thing it'll be ad hominems to get you to speak up. All right. Well, anyways, I guess Chris will have a chance to say his piece in March. And Robin, I think, also will have something to say about this. But bear that in mind, that at the end of the day, empirically, we compare quantum mechanics to reality in 2 ways. One is through the fact that we have this quantization of, I think it's typically bound observables. You get only discrete possible outcomes. This is actually what kind of first led the way towards the discovery of quantum mechanics. And secondly, it's the statistical component, that relative frequencies are predicted by the theory, and that these compared to the relative frequencies observed in the lab. And you can apply standard statistical comparisons to test consistency of the prediction with the observation. Yes, Rob?
I think that's really the big question here. Do you want Born's rule to be applicable in specifically experiments where you have at your access an infinite number of trials? Or would you like to be able to use Born's rule in other contexts, maybe?
So like single-shot experiments.
Or experiments where you only have 1 trillion trials at your disposal.
Oh, finite numbers.
Before we go further, who knows what Born rule is?
Well, I just defined it as the last slide.
I was just checking if you
Should be checking if he's paying attention. Yeah, so I think that's a key point, and I think we'll actually this course was given 5 years ago, and one of the things we didn't have is a careful discussion of probability, which is exactly why I asked Chris and Robin to address this topic, because I'm very interested in understanding it more deeply. So bear in mind, these are subtle issues, and they play a big role. Also, kind of an interesting anecdote is that, so of course, when Born wrote down his rule, he was dealing with wave functions on an infinite dimensional Hilbert space, some psi of x, and that actually in his paper, he proposed that it was the wave function itself, I think, that was the probability of an outcome, and actually added as a note in proof to the paper that actually it should be psi modulus squared to give the probability, which is, of course, the one that works correctly. And so it's actually funny that something so obvious that a complex number can't be a probability would have been missed. Yeah, I guess it was actually I guess it was after Schrodinger's paper. But anyhow, the point is things were kind of unclear in the early days. So actually, as we'll see later, that the first axiomatic formulation of the theory was written down by von Neumann in, I think, 1930 or 32, something like that. So it was well after Schrodinger's equation and Heisenberg's work that we had a nice systematic formulation of the theory. So composite systems, by the way, so I'm considering this to be a review for all of you, so I'm not explaining things in excruciating detail. Given two systems, which we'll label A and B, each associated with some Hilbert space. Here the word separable refers to the fact that there's a countable basis. And so we can think about orthonormal bases for them. We want to describe the composite system, or the joint system, also by some Hilbert space, which is what axiom 1 tells us. So what's the connection between these Hilbert spaces? Well, that's axiom 3, which is that it's given by the tensor product of the two Hilbert spaces. So I'm not actually convinced that this is not a redundant axiom. I mean, when you try and use quantum mechanics, I'm going to give you 5 axioms: preparations, measurements, composite systems via the tensor product, dynamical transformations, and measurement transformations. It'd be 5 independent axioms. So now you can't actually go and predict something based on that. There's a lot of things that go into the theory beyond these 5 axioms. So you have some situation in the lab. You have to know something about the fundamental forces involved. You have to guess or empirically determine what the Hamiltonian is. There's all these other inputs. So one way you might think that you don't need to specify the tensor product structure is to say, well, look, I know what I'm measuring on system A, and I know what I'm measuring on system B. So that means I have some association of measurements with self-adjoint operators. Now, similarly, you can say, and that's part of the implicit background information to apply the theory. Now, similarly, you can just say, well, part of that implicit background information might as well be what it means to do a joint measurement, which is that I take the tensor product of these observables. So it's not clear to me what to elevate to a formal axiom and what to demote to kind of background information that helps you make predictions. So any feedback on that from I mean, this is something I've gone back and forth on. I think every year I change my mind about whether or not this should be an axiom.
Your axioms to be, say, more mathematical or more physically motivated? That would be something that could be very easily, well, notions that could be physically motivated constantly.
Yeah, I think so.
But perhaps it's just a translation into mathematics?
Well, I mean, the other problem is that all these axioms are physically motivated in the sense that we found them through experiment. And so, yeah, I mean, it's ambiguous in my mind. But anyway, so given that, let's just proceed. So here's a little bit of just kind of elementary background for you, which is that the relationship between the dimensions of a tensor product between Hilbert spaces is just the product of the dimensions. Given that we have some basis for HA and some basis for HB, the Hilbert space HAB, which is the tensor product of the two, is spanned by the tensor product of the eigenbases of each one separately. And so any state in the larger Hilbert space can be expressed as a linear combination of these tensor product basis. And then just notationally, if we have finite dimensions, then it's these complex vector spaces. And just some terminology, we use the term bipartite to refer to a state involving 2 subsystems, and tripartite if there are 3 subsystems, and so on. And the Hilbert space of just a subsystem is called a factor space, not a subspace. So we have preparations, we have measurements, we can combine systems. Then the issue is, how do systems transform? Well, if we have some time interval between the preparation and the measurement, then, as you all know, the system evolves under a unitary transformation. So we have a unitary taking the state from time t1 to time t2. I do occasionally use the word state for simplicity of language. And we can write down the law that the unitary must satisfy as indicated in the second equation here, where it's understood that H is some self-adjoint operator that you've identified as being the energy function of the system, or the operator associated with the energy function. T is time, and the initial condition is that the unitary is identity when its arguments are equal. So from axiom 4, we get Schrodinger's equation as essentially a corollary. Now I wanted to have a little bubble here where Schrodinger says, why can't this be the axiom? And I actually don't know if you can go backwards, but it's cleaner this way. If anybody knows how to arrange pictures on the page using Beamer, please come see me after class, because I haven't figured out how to do that. I tried to use a wrap figure, and it didn't work. So is that the end of the story for transformations? Is that all we need, just unitary transformations? So it turns out, no. And this is actually one of the key issues where we get major debates amongst the founders of quantum mechanics. So the point is that if you do a measurement and you get an outcome, how do you describe the quantum system after the measurement? So von Neumann, when he wrote down his axiomatic formulation of quantum mechanics in the 1930 or 32, whichever it was, I always get the dates confused because I think he wrote it in German and then it was translated into English. And so I don't remember which date is associated with which. But so what he wanted to do was understand how do I determine what the state has to be? And so he actually used a thought experiment or a Gedanken experiment. And the situation he considered was the Compton experiment. So the Compton experiment is one where you have some electron coming in, and it scatters off of a photon at rest. Is it the other way around? Thank you. Yes. Yeah. Yes, thank you. So, so in the rest frame of a photon, yes, very nice. Okay. So what happens is now my lines are. Oh, well, let's go here. All right. So we have an electron. Nope. So now I'm really glad I didn't draw this figure in LaTeX. Here. At the end of the day, it doesn't really matter. All we have is we have particle A, and we have particle B. And there's some scattering event. Now, if we analyze this process using quantum mechanics, what you find is that there are many possible final outcomes for the momenta of the particles. So it could be that you find the first particle here and the second particle there, and it could be that you find the first particle here and the second particle there. So quantum mechanics actually predicts a superposition over all of these possibilities based on the initial input states. So what Compton said is, if I measure particle A and then determine its momentum by K prime, then by conservation of energy and momentum, I know what the momentum of the second particle B is going to be. Now, this is all to within some finite precision. So the point is, as stated here, that there's a statistical dispersion over the set of possible outcome states. But once I measure one of the particles, the dispersion is destroyed, and there's only one possible outcome or one, localized set of possible outcomes for the second particle. So if I want, now we said, okay, so I know that's the case. But now what happens if there's a finite time difference? So I measure this particle at some time, and then measure the second one at some later time, delta t. Now I know exactly what momentum I'm going to get for the second particle. So I know what state is going to predict that momentum. And that state is not the state predicted by the unitary evolution of this system. Because the unitary evolution gave me a statistical dispersion of possible states, of possible outcomes p prime. But after I know k prime, I can determine p prime, the Born rule won't work. The unitary evolution and the Born rule together won't work. So first of all, as a note to kind of experts, it's amazing the similarity between this argument and the EPR and Bell type arguments. And it was actually in von Neumann's book in 1930 or 32, whatever the date was. So it predates both of those. And so this is the point I just made, which is that von Neumann realized we have to somehow update the state after the measurement of the first particle to a new state that's consistent with the fact that we know with certainty that that momentum will be within some small range that's smaller than the original dispersion predicted by the unitary evolution. And he also realized, and this is something we will actually prove in a later lecture, is that this is not consistent with the usual unitary evolution. So we need a state update rule that's not given by the Schrodinger equation. And a first kind of shocking thing about whatever this update rule is that it's indeterministic. It's conditional on what random outcome we obtain in the measurement. And secondly, it's a discontinuous transformation because it has to be instantaneous, because delta t is unspecified. So delta t can be as short as we want, and the state has to transform from one vector to another vector instantaneously, basically. So while I'm not proving to you that it's not unitary, I think it's pretty obvious from those considerations that it's going to be impossible. So basically, it's by considering a filtering type measurement. What do I mean by a filtering type measurement? It's a measurement where you perform the measurement, you get an outcome, and then you want to describe the state conditional on that outcome. But moreover, it's one where we're actually describing a particle which is undisturbed by the physical process of measurement itself. So this is called a filtering type measurement. I didn't explain that extremely well, but it'll become clearer later. So basically, von Neumann concluded that we actually need two dynamical laws in the theory. And ironically, he chose the first one, which he called process one, to be this state update rule. Namely, that after some measurement of an outcome, the system is left in the eigenstate AK associated with the detected value. So it's this transformation, which is in general from superposition over states to a particular state. And that which particular state you transition to discontinuously is randomly determined by the outcome itself. And then process two, so don't ask me why he calls this 2 instead of 1, is Schrodinger evolution. So then it gives us our fifth axiom for quantum mechanics, which is the projection postulate, which is just basically process one. So this is an extremely controversial part of quantum mechanics. It's called the reduction of the wave packet or the collapse of the wave function, and it's caused innumerable people to lose innumerable nights of sleep. And just to kind of give you one thought, so von Neumann really saw, he really struggled with the notion of this process one and saw it as an essential randomness in nature and considered it grounds for abandoning what he called the principle of sufficient cause, which I guess is what you say in the 1930s to say causal determinism. It's not entirely clear. I don't have a Rosetta Stone to know what he meant by that. But basically, the idea is that Schrodinger evolution is deterministic. So if I know the Hamiltonian and I know the initial condition, I know the final state vector. But here, the state vector under this process is indeterministic. So it's not causally determined mechanism. So I'll actually provide you with some quotes from von Neumann, and we'll discuss this in great detail. But so for now, today's lecture and part of the next lecture is just to really go through the axioms and leave some of this more interesting conceptual business for a later lecture. Yeah.
Transmission, or there's two types of updating going forward. Heisenberg used his matrix theory without noticing this.
I don't know. I'm not a historian of the thing, so I don't know really. I think from reading von Neumann's book, which I read 5 years ago when I prepared the first version of this course, he didn't credit anybody else. He just said that this seemed like something he came up with, and to me, it seemed like he came up with independently. I would not be surprised if Einstein realized this first, though, because most foundations seems to me to be a footnote to Einstein. Yeah.
Still on the topic of axioms, and you brought up what's the difference between an axiom and background that goes into the theory.
Yeah.
I was wondering what should be the role of time in quantum mechanics, because it's not really talked about that much. But this is, as far as I can see, is with background that you put a t into the, and then that's what enables you to have your axiom 4, right? Which so it seems that that axiom is highly, and also the fifth axiom is highly dependent on your understanding. So what is time?
I need the answer to that. Yeah, no, I mean, obviously in quantum mechanics and non-relativistic, well, actually, in both cases, it's just a parameter of the theory. So it kind of flows in a Newtonian sense, independently of everything else. So
The number that a classical clock will predict.
yeah, I would provisionally just say, yeah, that's the way to think about it in this study. Which is unfortunate. I mean, this ties into, obviously, some of the motivation I raised in the first couple of slides about you really want a more sophisticated notion of time that's consistent with general relativity.
Even without general relativity, I mean, you're talking about time, right? And so you have these classical clocks that are already playing a preferred role in the theory, I think, or at least it seems to me that way. And you haven't even brought up general relativity or anything else.
Yeah. Yeah, well, I'm certain I'm just going to treat it as a primitive, and that's not an issue I'm going to, delve into. So, okay, so that for me is you can do, you can be a quantum technician with those axioms. Now, it's worthwhile though thinking about how to describe quantum mechanics in a more general setting where you don't have idealized information. And it turns out it's a little more subtle than just taking convex combinations of things. And so that's kind of what's interesting to me about the generalized formulation. And there's, as we'll see in the next few slides, there's a very subtle relationship between the idea of classical lack of knowledge about, say, which state was prepared, which gives you kind of a mixture of possible states, versus having some entanglement between your system and some other system and tracing over the second system to get a reduced description of the system of interest. And that arises differently in preparations and measurements and in transformations. So let's talk about how to describe states in a more general setting. So just a simple scenario is imagine you have some state vector associated with some preparation 1, and you have another state vector associated with a preparation 2. And each of those are prepared with probabilities P1 and P2 respectively. So how can we describe that kind of effective situation? So you can just refer to the Born rule and infer what the state should be. So suppose we're just measuring some arbitrary operator A, and it has eigenvalues and eigenspaces as specified. Then the probability, given preparation 1, of observing outcome A is the trace of the projector onto A's eigenspace against the state psi 1. And similarly for 2. Now, if you don't know which preparation took place, then you just add the probabilities convexly. So the probability of A is just the weighted probability P1, the weighting probability P1 times the probability of outcome A given preparation 1, plus the weighting probability P2 times the probability of getting outcome A if you prepared state psi 2. But the trace rule is linear, and so we can just write down an effective operator rho, which is given by the convex combination of the two projectors. Yep. Okay, point well taken. So P1 is the relative frequency of preparing preparation 1. And yeah, so notice that instead of putting relative frequency directly into the Born rule, I just define the term probability as relative frequency. Right? So I can use the term now. I should also define state to be preparation procedure, so I can freely use that as well. And so what you find is that because P1 and P2 are relative frequencies that add to 1, is that trace of rho has the following normalization. And that gives us conservation of probability. So you can construct general quantum states via convex combination in general. And in the discrete case, you just take a sum over these probabilities. And in the continuous case, it would be an integral. Now, the other way you can get a situation where you can't describe your system with a pure state is let's just imagine that you have some pure state psi, a projector on the psi, in a Hilbert space HAB. And then, but you just want to describe system A. So actually, it's quite similar to this situation. So I have a system A and a system B. Now forget about the measurement and say, okay, you know what? I don't care about particle A anymore. I just want to describe particle B. So I'm not taking any information about measurement outcomes here. I just want to describe system B now, or vice versa, system A. Then the relationship for doing that is the partial trace. And the state rho A is the reduced state. So now the partial trace is something which I covered in the fourth year quantum course, and I expect the graduate students to know, so I won't define it. But just quickly point out that you can determine that this is the unique way of associating a state with a subsystem by demanding a consistency of, so here the expectation of A is just the oops. And the expectation of A tensor identity, where this is system A and this is system B, is the trace of A tensor identity against psi, where this is understood to be an element of HAB. More actually, well, this is a projector onto HAB, so it's a linear operator acting on the Hilbert space. So the idea is that, how do I figure out what rho A is? Well, I know that this is true, and then I demand that these two things be equal, and that specifies what rho A has to be. Yeah.
So like this physical consistency because the operator A tensor identity is like measuring measuring A on one subsystem and doing nothing to the other subsystem.
Exactly right.
So that's the kind of joint description, but
Yes.
you want that to be the same as just the single system description.
Yes. Right. And so from that, you can deduce what rho A is from that constraint. And then actually, I think I've written out here what the partial trace operation is. Basically, the matrix elements of rho A, denoted by L and L prime, is given by summing over the matrix elements, sum of the matrix elements in the larger density matrix. So the partial trace works for any operator, not just the state, and it follows the same rule. Namely, while here we defined it explicitly, if L and K are eigenbases for Hilbert space HA and HB, then the partial trace involves basically summing over the expectation of the operator in the state in K, and then looking at each of the possible matrix elements LL prime. And so the important thing to realize mathematically is that unlike the trace, which returns a scalar, the partial trace returns an operator. So it takes an operator on a bigger space and gives you an operator on a smaller, acting on a smaller space. So we could generalize axiom 1, which is, which I didn't actually motivate this as well as I could have, but the physical configuration, I don't know why I use those terms, the preparation on a Hilbert space is associated with a positive semi-definite operator rho, subject to that normalization. So remember that positive semi-definite means that the operator is self-adjoint, and UPU is greater than or equal to 0 for every vector in the Hilbert space. And positive semi-definite basically means non-negative, but sometimes people just call it a positive operator. Yep. That's very nice. Yeah, it does. So yeah, the non-negativeness assures that we have the probabilities, and the trace assures that the probabilities add to 1. So then we want to, once we have a generalized notion of state, we say, what do we want to recover pure states, these idealized preparations? And that's basically, there's 3 ways to determine that. One is to check that the self-adjoint operator rho with any valid density operator squares to itself. The second condition is to check that the trace of rho squared is 1. The third condition is that you can find some projector that's equal to rho. And those are 3 equivalent ways of determining if a general state operator is pure. And pretty soon, oh yeah. So if rho cannot be expressed in that form, if any of these 3 conditions are not met, then the state is called mixed. So here we get some kind of philosophical jargon. So now we've seen 2 ways you can get a mixed state in quantum mechanics. One is through some stochastic process that generates pure states with some probabilities, and the other is that you have some generally entangled operator on systems A and B, and you take the partial trace. So it turns out any valid state operator, that is a non-negative operator with trace 1, can be expressed as a convex combination of pure states, which means it could have been constructed physically by this stochastic procedure on the Hilbert space you're interested in. But it's also the case that any valid density operator can also be constructed kind of operationally by constructing some entangled pure state on across systems A and B and partial tracing out system B and getting a mixed state on system A. So the idea is if I give you some state and you do a procedure called tomography to identify it, then you can't know, based on knowing rho, what method was used to construct it. And so philosophers refer to mixed states created by a convex combination as proper mixtures, and ones obtained by a partial trace on an entangled state as improper mixtures. The distinction is purely philosophical, though, because they're mathematically and operationally indistinguishable sets. Now, what's interesting is that's not going to be the case for transformations in POVMs, generalized transformations and generalized measurements. So, OK, at some point now, my notes are just going to end. So I don't know exactly when that's going to be. So the pure state. So now the opposite procedure is the following: given some density operator on Hilbert space A, how do I find a pure state on a larger Hilbert space that's consistent with that density operator? And this is called a purification of the density operator. And so I guess an obvious constraint is that that the dimension of the Hilbert space of the second Hilbert space has to be at least as large as the rank of the state, namely little m. And moreover, the purification is not unique. So if I find some purification psi, I can just act on it with identity tensor U, some unitary transformation in the second Hilbert space, construct a new state psi prime, and taking the partial trace, I will get the same rho A. So rho A prime, so to speak, will be equal to rho A. So there's a freedom. So there's actually a continuous infinity of possible purifications. OK, that's where we end. So OK, so we'll stop now, use the remaining time to take care of some logistical issues. And yeah, go ahead.
Last 2 slides. If we can think of processes that produce, I guess, proper mixtures as entanglement machines that basically entangle the system of preparing with some larger system, those generate those kind of classical mixtures.
Yeah, I mean, I guess at the end of the day, you imagine a stochastic process as being some coin flip or something. And you can think of that as some kind of classical system. But at the end of the day, it can be described by quantum mechanics. So the machine which is producing stochastic combinations is really some other Hilbert space that's involved in the process. Is that what you're
kind of, yeah, because the machine is entangling the, well, I guess our system, we think of it as producing stochastically with some larger system, and that just by the equivalence of the two.
Yeah, so the issue, so I agree, but it's not clear to me that it would require actual entanglement between this kind of classical Hilbert space. This Hilbert space where the system is behaving classically, it's creating the coin tosses. I think I know the answer, just not obviously off the top of my head. But yeah, so there could be an actual distinction in terms of whether there's entanglement, whether entanglement is required. Like, can't prove it to you off the top of my head. Yeah.
Would it depend on if we had more information about the system, like post-selection, post-selection technology, the system after the entanglement, or after the interaction?
Yeah, I don't know if I'm mad. So, yeah, I'm kind of thinking now maybe the distinction is maybe depends on your interpretation. So Bohr, as we'll see, Bohr really demands that the way we understand quantum mechanics is that you have classical apparati, and those define the procedures you do, and that we never treat those quantum mechanically. And so he kind of insists on this divide. And so maybe this distinction depends on that kind of an arbitrary divide. So I'll criticize that view, by the way, of course. And I'm not sure if this distinction depends on that divide. I think people have to think about it. So I'll get back to you. Okay?
So we can write any mixed state as a convex combination of pure states, right? But we can't do that in a unique way. That's correct, right? So, but if we start off with a finite dimensional Hilbert space, there are only countably many pure states. Is that true? Just because
if the bases are countable, well, for a finite dimensional Hilbert space, bases are of course countable.
Right.
But you have, continuous parameters, coefficients. So you can write any state, even a two-level system, can be expressed as C1 plus C2 where C1 and C2 are complex numbers. So you have a continuum of possible states in a two-dimensional Hilbert space.
But in terms of what we measure, C1 and C2 can just be rational, right? Like any measurable pure state is like equivalent to some.
Well, they're complex
C1
numbers
C2.
first of all, so that rules out rationals right
Oh
there.
yeah, of course.
But yeah, I'm going to refine my postulate too. Yeah, no, so these are arbitrary complex combinations.
Okay, so I guess that kills the second part of
But
that.
no, but there is actually a continuous infinity of different convex decompositions in any mixed state.
Okay,
So it's a continuous set of possible.
okay. That's because I was wondering then.
So that actually may be an exercise on the assignment.
Yeah, because if you had
I think it's an exercise in my open quantum systems course. Yeah.
So while we're talking about countability and accountability and all that, I have a mathematical question related to that. So when you say that we're looking at Hilbert spaces that are separable, where you take separable to mean they have a countable basis, how is that related to the analytic definition of separable, where a space is separable if it emits a countable dense set?
I don't know, but they might just be independent notions.
They're the
Unless
same.
they're equivalent.
They're the same.
Equivalent. Yeah, okay.
I guess that's what I'm asking. In what sense are they?
Yeah, I don't know. I just know the first definition of separable. So.
A separable Hilbert space is separable in that sense. If it has a countable dense basis, then it admits a countable. Sorry, if it has a countable basis, it admits a countable dense set. If and only if.
Thank you, Robin. Please go ahead.
Sorry to go backwards, but I don't understand the question.
Okay, so I'll just repeat. So we were, in the beginning, we were considering our state vectors to live in a Hilbert space that was separable, where we took a separable Hilbert space to mean it has a countable basis. But in analysis, you also, or topology, you also have a notion of a metric space being separable if it admits a countable dense subset. And a dense subset is if like Q is dense in R because you can get arbitrarily close to any real number with a rational number, so Q is dense in R. That's what the analytic notion of denseness is. And I wanted to know how that relates to separability and linear algebraic sense.
So when you said they're equivalent, you meant equivalent in the context of the Hilbert space, I suppose.
I hope a separable Hilbert space. A Hilbert space is separable in the sense of having a countable basis, if and only if it is separable in the sense that, you know, the standard metric space. So every separable Hilbert space has a countable dense subset, and non-separable Hilbert spaces do not.
Yeah, Victor?
So as long as we're being topological, I think on your fourth slide, it was like right at the end of when you stated the first simplified postulate, you said that there was I think an equivalence relation between pure states and So the last thing there is the state vectors have a complex phase, is physically insignificant, yada yada yada. But the only form in which I'm familiar with the complex projective space is as the set of lines in R. I only know that it's basically like a set of lines.
Here it's just a set of rays in Hilbert space.
Okay.
So we mod out the U1 phase.
Okay. So.
Okay, so I was actually talking about this with the students the other day, and so it's essentially you can also think about it as being one-to-one correspondence with the projectors onto the Hilbert space.
Oh, okay.
But I mean, so you want to get rid of your normalization first of all, and then there's still an arbitrary phase factor within that normalization, and you want to get rid of that too. And so when you mod those things out, so I don't know much about the complex projective space beyond how it arises in quantum theory.
In none of the axioms was it stated that there's this fundamental randomness, and none of them seem to imply it. So what did von Neumann, why did von Neumann sort of come to that conclusion? Like, it seems to be to use the axioms and be a practitioner of quantum theory, you don't actually need to use the fact that there's fundamental randomness.
Yeah, so we're going to go through this in detail, exactly why von Neumann concluded that. But it comes down to, he actually is one of the, I guess, signatories on the, what's called the orthodox interpretation, which is, some people use orthodox interpretation to mean the Copenhagen interpretation, but I prefer, following, I guess, Boom and others, to refer to the von Neumann-Dirac formulation. And that formulation takes, and we'll see this in detail, it takes the wave function to be essentially an element, an ontological element. And so the fact that you have this discontinuous transformation, which has a natural meaning in classical probability theory, you elevate it to this ontological primitive, and it means you have to assume there's fundamental randomness. So it definitely was you're right in that it doesn't follow from any of the operational axioms. It just followed from his beliefs and ontological commitments that he had made, which he didn't have to make. And so we'll go through that. You guys all comfortable with me throwing around the term ontological? How many of you have not heard that term before?
I've heard that.
So basically what it is, it's like, Greek study of words. So it's ontos. And we'll contrast it with kind of an epistemological point of view, which is where elements represent knowledge as opposed to objects with properties. I'm glad everyone's asking so many questions. We have about 10 minutes left, so maybe we should turn to the logistical stuff, and we'll come back to the technical issues next class. So for logistics, so as you hopefully have realized by now, the course will be held on Tuesdays here from 2:30 to 4, and on Thursdays at IQC from 2:30 to 4, 2:30 to 3:50, strictly speaking.
Trek to IQC.
Yes, it does. Brave the elements. So now, for the students on campus, there's a shuttle set up And so the shuttle, okay, I'll have Monica put the contact number. We actually use a phone number you can call to take the shuttle. But we have reserved the shuttle for these times to take you from kind of the center of campus, just outside of the EIT building. It's the one with the dinosaurs in it. That's how I remember it.
And that's not referring to the truck who are.
So every building on campus. So the idea is this. There are several students who have told me they have class ending at 2:20. So actually, by a show of hands, who has a class ending at 2:20 on campus? Only 4 of you. That's wonderful. Okay, so the 2:25 shuttle is reserved for you guys. If you see anybody else on there, you just kick them off, okay? Unless there's space. Because the idea is if you don't have class at 2:20, then please take the earlier shuttle at 2:05, or just arrange your own transportation, or walk and enjoy the winter landscape. So there is an earlier shuttle at 2:05, but the shuttle only seats like 4 or 5 people. Did anybody take the shuttle here today? Yeah. It seats 6. All right, good. So yeah, so basically then I think we're okay. And then the shuttle will be available after class at 3:55, which is in 7 minutes, to take you back to campus, for those of you who want to go back to campus. And I guess that's first come, first serve. So what was the other?
Yeah, I can give rides from RAC to here on Tuesdays, but you find your own home.
Yeah, so the other option would be to go from RAC to main campus and take the shuttle at 2:05. Okay. I guess that's it. If that's transportation issues sorted
I
out.
have a question.
Yeah.
Is there a parking lot at RAC is IQC?
Yeah, that's a good point, actually.
Is there a parking lot there that we can use?
Yeah, I was going to do that. You get passes from the. If you drive, I mean, the reception will give you a pass for the afternoon.
So how many would drive with their car? 1, 2, 3. So we'll organize something with reception so you can get in and get a pass. Or if you pay and keep your receipts, it's $3 each. If you go in, if you pay, keep your receipt, then we'll pay you back at the end of the day.
So actually, the other thing is, how long is the walk?
How long is what?
How long is the walk?
From here to so it depends how fast you walk.
35 minutes,
Yeah, about 25.
40 maybe?
The sidewalks on there's West Graham Way, they don't get cleared in winter usually, so.
So you have to charge. So it's not ideal.
Yeah.
Now, all the lectures, so these lectures, obviously all the PI lectures are recorded. We have set up for recording the lectures at IQC. Now, students have to participate. It's part of the evaluation. It's very important. But if you do miss a lecture, you can catch it online. So I don't know. We'll have to figure out exactly the lectures will be posted within the PI system, or if we'll have independent postings on the webpage. I'll let you know how that's going to work out. By the way, so IQC doesn't have built-in cameras, so there will be kind of like cameras for the next lecture, so don't be too intimidated. Be sure to shade or whatever. And the other thing I want to bring up is what course you're registered in. So this is the graduate version of the class. If you're an undergraduate, you should be registered in either the AMAP or the physics section. If you're a graduate student, you should be registered in the 900 level version. So the difference is that there will be additional assignment problems and a much higher standard for the report for the grad students. So the final report will be something along the lines of 10 to 15 pages on the topics people suggested. Come see us for confirmation of the project you want to work on. And we're quite flexible as long as it loosely relates to the topic of the class. But I noticed there are some undergrads registered in AMAP 900. Please come see me if you think you have a really good reason for doing that. Otherwise, you should be registered. These two are equivalent, basically. I think you were the one, actually. So we should talk about that. So I guess that's it.
Do you have any questions?
Just in terms of the start time, I think if the course starts at 2:30 on the dot, then people coming from campus will be there.
Yeah,
So
we'll
we'll
try
probably
to do, now that we can roughly spot the ones who have a course at 2:20, we'll wait for you guys to, let's say 2:35 or 2:40.
I think the shuttle takes about 7 minutes or something like that, so the shuttle will be tight, but we'll start 5 minutes late then. So as a rule, we'll start 5 minutes late to accommodate that.
And I also wanted to mention that you may wonder why these things are recorded. So Joseph and I have a project, which is one of these long-term things, to turn these lectures into an ebook. And we had a version of this course in 2005. We have a version now. We want to bring everybody around the world. The lecturers who are going to come and talk to you are well known around the world for their to be proponent on certain interpretation of quantum mechanics. And we would like to bring all of this together. And this would be a state of what people are thinking about interpretation of quantum mechanics at the beginning of the 21st century. So this is a grandiose project. We are part of this, so we immortalize it. Not even the ebook will come out, but that's part of the reason why we wanted to try this now.
Yeah, and on that topic, so we offered the course 5 years ago. I think you have to access this by a direct link. Maybe we'll put the link in the current web page.
Yeah.
And so this was the previous version of the course. All the lectures and the videos of the lectures are available online. So the first 3 weeks were, again, kind of myself covering the introductory material. We had David Wallace speak about the many worlds interpretation. And these, I think, are PDF files with the lecture notes here. And some suggested reading. We had Shelley Goldstein, who was Roderick's supervisor, talk about the de Broglie-Bohm interpretation. My former PhD advisor, Liz Valentine, spoke about the statistical interpretation, which I will kind of cover briefly myself. And then spontaneous collapse models, which we don't have this term. So we had Philip Pearl talk about spontaneous collapse models. The other famous version is the GRW scheme for Girardi, Rimini, and Weaver, or something like that. So basically what these people do is they take essentially the von Neumann-Dirac point of view seriously, which I'll describe that to you. They take it literally. They interpret the quantum state to be literally real. And then then you confront certain paradoxes and problems when you take that point of view. So rather than just abandon the assumption that that was an unreasonable interpretation, they actually change the mathematical structure of the theory to accommodate the interpretation by adding a nonlinear term so that the state kind of spontaneously localizes, so that you can't have large-scale superpositions. So it's not an interpretation per se, but rather a proposed modification of the theory to accommodate certain interpretational prejudices. As you can see, I'm not a big fan of it. So Anton Zeilinger came and gave some very nice lectures. The first was on experiments he did demonstrating coherent superpositions of very large molecules called buckyballs, and even larger. So showing that you can have essentially a double slit type experiment performed on very large systems, and everything works kind of as expected. And he gave a second lecture on his views about interpretation. Robert Griffiths, who's the founder of the Consistent Histories view, spoke about that. You can see those lectures online. Still doesn't make sense to me, even after that. We had LASP come and discuss his seminal experiments demonstrating non-locality, or more precisely, violation of Bell's inequality, and explaining the significance of that. We had Lucian Hardy, who's at BI here, discuss his axioms, his axiomatic operational axioms for quantum theory. The motivation for that is, you look at the axioms for quantum mechanics as we saw today, and they're very kind of mathematical, right? So you just posit a Hilbert space and posit self-adjoint operators. And the idea is to try and come up with operational principles, or physical principles more precisely, that imply the axioms of quantum mechanics. It's kind of very much inspired by the way that, say, relativity is implied by physical principles, such as the speed of light is constant in all reference frames, except in the Compton experiment. And Matt discussed about the quantum logic approach. We will, however, have Alex Wiltshire this term talking about this convex sets framework, which my student Cosmin is an expert in. And that's kind of a generalization of what Lucien has done. So it's a very mathematically formal approach to looking at classes of theories, of which quantum mechanics is a special case. And then Anthony Valentini spoke about the possibility of observing deviations from quantum mechanics if you assume there are a certain kind of hidden variable theory. And I've talked a bit about the epistemic interpretation, which I'll do also this year. So anyway, so have a look at those lectures. If any of them intrigue you, if you want to make suggestions for this one open week we have, because we still haven't recruited somebody, so we're sending out some last minute invitations. So if you have any suggestions for a topic you'd like to hear about, we'll do our best. But my personal preference at this point is to have someone talk about many worlds, because it's such a dominant point of view, and it's one which, you know, I basically don't buy at all, because I refuse to say anything positive about it. But I think in fairness to you, you should have someone come here and speak about it, and maybe it'll make more sense to you. Okay, great. So we'll see you on Thursday at IQC.